followed by a 10 to 15-minute interactive session where you will have the opportunity to ask questions and engage in discussion with our distinguished speaker, Dr. Soham Sarkar, Assistant Professor at the Theoretical Statistics and Mathematics Unit of the Indian Statistical Institute, Delhi. Dr. Sarkar has an impressive academic background, having completed his Masters in Statistics from the University of Calcutta and PhD in Statistics from the Indian Statistical Institute under the supervision of Professor Anil Kumar Ghosh. He is recognized for his expertise in functional data analysis, high-dimensional data analysis, non-parametric statistics, and statistical learning. Dr. Sarkar's academic journey is complemented by his extensive research experience, including a postdoctoral fellowship at the EPFL. His work has been widely published in leading journals, including the Journal of Statistical Society Series B and Biometrica. His contributions to the fields of high-dimensional data and statistical learning have garnered significant recognition. He is also a recipient of the Inspire Faculty Fellowship from the Department of Science and Technology, Government of India. In today's lecture, Dr. Sarkar will delve into covariance estimation for functional data. I thank you, Dr. Sarkar, for joining us today. I would now like to request you to begin your presentation, sir.
Okay. Thank you very much for this really elaborate introduction, and I am kind of flattered to hear all these good things about myself. So today I'm going to talk about covariance estimation for functional data. And am I audible? Everything is fine, right? You can hear me clearly?
Yes, sir.
And
yes,
you can
sir.
also see my slides?
Yes, they are clear. Perfect.
Yeah. Okay. I'm going to talk about it, and I will just discuss about covariance estimation, and then I'll talk about some things that I have done. And I'll be very happy if you stop me in the middle and ask me questions. Okay. So if you are, if something is not clear, you can always stop me and ask me questions in the middle. Okay. And this is most of the talk that I'm going to deliver. So it's based on a joint work with Professor Victor Penardos from EPFL. So most of these things were done when I was at EPFL as a postdoc. And it is supported by Swiss National Science Foundation grant. So let me start, okay? So let me start by giving some examples. Examples of functional data. What are functional data? And so this is one particular example. Here we have the following. We have temperature recorded at several, so we have here the months, and here we have the temperature, okay? So starting from January, February up to December, and then again January. And we have the temperatures recorded at a particular weather substation, and there are several such. So each curve here represents the temperatures that were observed at one particular weather substation, okay? And we have several such substations, and hence we have several such functions. So this is one example of a functional data. Here is another example. So FDA, so F, D, and A, this has been written by several people. And this handwritten FDA words, these are, so for one person, we have this F, D, and A, okay? And this is written by several people. So we have several such copies. And this is another example of functional data. So FDA, why this? FDA stands for functional data analysis, and that is why this is written. Okay, but there is nothing particular about F, D, and A. It could have been something else also. This is another example. So here we again have something like this. We have one axis here, another axis here, and for each pair XY, we have a value fxy, okay? And this is one particular instance of this kind of a function. So what kind of data is this? This is the stock price of different stocks. So stock price, and there is something called, okay, so I'm not an expert, so I won't delve into that. But here we have the purchasing price of a stock, at a given point of time. Okay. So we have different stocks over time and then purchasing price at different points. So if, forget about that. We have 2 points xy, and for each point pair xy, we have a function fxy. This is one function, and we can have several such. Very good. Here is another example. This is brain scan. Okay, this is what is known as fMRI or MRI scan. Uh, so what we were seeing, this is the slice of, so the brain is imaged using this MRI machines, and then we have the three-dimensional picture of the brain, and what is being measured is the water content in the brain at different parts of the brain, and this is used to detect whether there is the functioning of the brain is going as it is supposed to be, or whether there is some kind of activation at different parts of the brain, etc. So that is a 3D object because our brain is a three-dimensional object. And what you are seeing here is the cut of that three-dimensional object from over the z-axis. So we cut the picture from this side onwards. So starting at the top, this is the top portion, and then we move on, and here we have the bottom part, etc. Here also, if you think about it, we have the 3D brain, and at each part of the brain there is some water content. Okay, so if you look at the water content, you can say that that is the functional value at the point xyz, where xyz denotes the point in the xyz plane corresponding to that brain cell. Okay, so all these are functional data. So what is really a functional data? Functional data corresponds to data analysis where the observations are functions. Okay, so the observations that we make, in the first instance, it was the temperature that we observe. So temperature is a curve. It is a function. It is a function over the time point. Okay. In the second example, we had FDA. So someone is writing F, someone D, A, etc. So you can say that the pressure that someone is putting on the paper, that can be measured, and that is a function of several things. So for instance, the time point at which the person is writing it, and also the place where the thing is being written. So you it's easy to understand that the pressure that we put in this part is not the same as the pressure we put in this part, and not the same as the pressure we put in this part, and so on. So the pressure that we put on the paper is a function of the location at which the pressure is being put. Okay, so that is also a function. In this case, it is a function over two-dimensional domains. So we have x, y, and for each xy, we have a function fxy. And in this case, we have a function over a three-dimensional domain. So for each xyz, we have a function fxyz. And one observation for us is one function. Okay. Now, functions, as you may know, some of you may know, functions are infinite dimensional objects. So they are not finite dimensional, like we study in multivariate statistics. So that is a challenge. Okay, so that is a new kind of difficulty we have to manage with this, how to tackle infinite dimensional objects, etc. So that is one of the goals of functional data analysis. So what we are going to assume, so we have some functions, and there are several function spaces. Okay, so for studying these objects, for doing something with them, we have to assume that they are elements of some function space, and we are going to assume that they are elements of a Hilbert space. Okay, in particular, okay, so if you know what Hilbert space is, very good. But if you don't know what a Hilbert space is, so Hilbert space is a space on which we can talk about inner products. Okay, so that is a space on which we can talk about inner products. In particular, we can also talk about orthogonality, etc., which gives us some additional benefits. So we are going to assume that. So this is not the only assumption that is made. Sometimes people also assume that these are elements of what are known as Banach spaces. So Banach spaces are spaces on which we don't necessarily have inner products, but we have norms. Okay. But we are not going to deal with that. We are going to assume that these are elements of a Hilbert space. Now, there is also something else involved in functional data analysis. So we understand that data are curves or functions or surfaces, etc. But in practice, we can never observe a curve fully. Okay, we never observe. So although I showed you uh, the temperature curves, we never observe the whole temperature function over the whole year. It is measured discretely over time. Maybe every 5 minutes or every 10 minutes or every hour, every 6 hours, etc. But it is measured discretely. Okay. Similarly, there are other examples. For instance, you have seen ECG curve. You have seen this picture of this brain. So although these pictures, they look like a continuous function, but in practice they are not, because think about it. If we want to uh, store an infinite dimensional object, a whole function, that is infinite dimensional, and the reason behind that is it is not possible to completely denote or completely specify that thing using finitely many numbers. Okay, so that means if we want to store one function, we want infinitely many numbers. We have to store infinitely many numbers, which is not possible. Even if you take a supercomputer that has a finite memory, so we cannot store infinite objects. So in practice, we observe things discretely and we have to deal with that. Okay. So I'll talk about these things in details in the next few slides. So we are interested in covariance estimation. So this is what our setup is. So we have x1, x2, xn, and I haven't used the usual x notation because these are functions. Okay. So that is why we are using this rather stylistic x to denote this. But we assume that they are IID. So they are still independent and identically distributed. And they have the same distribution as x, where x is a function. X is a function which looks like xu. U is the index. Okay, so for the first example, for the temperature curve, u was just the time points at which the temperatures were observed. For the second example, it was the location of the writing. In the third example, it was the xy coordinate. In the fourth example, the brain example, it was the xyz coordinate. Okay, and we assume that this u, the index, it is in 0, 1 power d. So it is possibly a vector. It is a d-dimensional vector, and all the components are between 0 and 1. Now, about this 0 and 1, it is not necessary to assume this. We can always assume that it is on a compact set. It takes values in a compact set over Rd, but saying that it takes values on a compact set in Rd and saying that it takes values in 0, 1 power d, there is no difference. I mean, theoretically, there is no difference, and even practically, there is no difference, because we can always convert that compact set and take a transformation and go to 0, 1 power d and back, and we can go back and forth. No problem in that. So we say that it's taking values in 0, 1 power d, and d is possibly greater than equals to 1. Okay. And I said that we will assume that the functions are taking values in a Hilbert space. In particular, we will assume that they are taking values in L2 space. Okay, so if you know what L2 spaces are, very good. Otherwise, L2 spaces, yeah, L2 space. So it is space of all functions f such that we can integrate the square of the function. Okay, and we are saying that it is being done over 0, 1 power d. Okay, so this is our L2 space. So one good thing about this space is I told you that this is the Hilbert space, And on this space, we can define what the notion of inner product. So inner product between two functions in this L2 space is defined as we take f, we take g, and we take their product and integrate it. Okay. This defines an inner product on the L2 space. Okay. Uh, so all the properties of an inner product are satisfied with this function, and this has some additional benefits, which I'll some of them I'll talk about. All right. Okay. Now, when we have this function space, it is also possible to talk about the notions of expectation and variance. For instance, what is expectation? Expectation is defined like this. So expectation is defined. So there is a notion of expectation. I cannot tell you what expectations are, but if you know what Lebesgue integrals are, then there are ways of extending Lebesgue integrals to general Hilbert spaces or even Banach spaces. And with that, we have a notion of expectation. And we assume, because we are trying to estimate covariance, we assume that the expectation is 0. There is no loss in defining that, because if we don't assume that the expectation is 0, what we do is we first center the observation. So instead of working with x, we work with x minus x bar. Okay. Similarly, variance is defined as the expectation of x cross x. Okay, so this cross with a outer circle x. What does that mean? So, if you have, so let me just give you an analogy with multivariate data. You know that if you have a vector x whose components are x1, x2, xd, or rather xp, then its expectation is defined as the vector with expectation x1, expectation x2, expectation xp as the components. Okay. Similarly, if we look at the covariance, or the variance covariance matrix, the dispersion matrix, the covariance of the vector x is defined as the expectation of x minus expectation of x times x minus expectation of x transpose. Okay, this is how the covariance of a vector is defined. So this is the outer product. This is the outer product. And we take the expectation of the outer product. Okay. Now the element that we have here, this element, this element, this element. So x cross x, it is defined as the outer product. So what is the outer product? If you think about it, if we look at the outer product here, if we take, say, two vectors x and y and take their outer product x y transpose, then what happens is if we multiply this by another vector z, then we get y transpose z times x. Okay. Now the same thing is used to define this outer product. So if we have two functions f and g, then f cross g is defined as, if we take another function h, then this will be the inner product between g and h times f. Okay. So this is integral gu hu du times fu. Okay. And this is how this cross is defined. Now, I believe many of you have studied time series, but if you haven't, for time series, we have two things. We have x, which is indexed by t and omega, where t denotes the time index and omega denotes the variability or randomness. Okay, so there are these two indices. And if we fix omega, then we have a function xt, which is the time series that we observe. And for a fixed t, we have x t omega, which is a random thing for each t. Okay, and for a time series, we need something called a joint measurability, etc. But if you think about it, for a time series, we can define components-wise expectation of x at t for each t. And if we now take a function whose value at the point t is the expectation of x at t, that is defined to be the expectation of the function or mu t. Okay. Similarly, if we take the covariance between xt and xs, that function, that is a function of s and t, that is what is known as the covariance function of the process of the time series. Okay, the, it is the same kind of thing. So this expectation is similar to that. So we are taking kind of the coordinate wise expectation. Similarly, the variance, we are taking the coordinate wise variance, all the possible pairs of coordinates, but not necessarily. I mean, there are some conditions. So this joint measurability condition is needed in order to have this. Even when we don't have joint measurability, it is possible to define the expectation and the variance. And our target is to capture the variance C. Okay, so the element which is the expectation of the outer product. Now, whenever we have this thing, we have this covariance C, there is a corresponding kernel. Okay, so the kernel, so this C is what is known as an operator, and this operator has a associated kernel to it, and the kernel is what I just defined. It is C at uv is the covariance between x at u and x at v. So we take a pair uv and we look at the covariance between x at u and x at v, and that a function now which is indexed by two things, u and v. So this is a function over 0 1 power d times 0 1 power d, and we are interested in finding c. But what happens is this c and the kernel c, they are equivalent, meaning that we can go from one to the other and so and vice versa. So there is no loss of generality in trying to estimate this kernel C. It's the same thing. Okay. So we want to estimate this operator C, the covariance, or equivalently, we want to estimate the kernel C. Okay. Covariance estimation is a fundamental problem in statistics. So what I am going to discuss, it is a fundamental problem in statistics. And it is perhaps the second most fundamental problem in statistics after mean estimation. So whenever you have data, first you try to measure the central tendency, which is the mean or the median, etc. So first you try to estimate the central tendency. Once you have done that, the second thing that you try to estimate is the variability via the covariance or other dispersion measures. So this is the one of the most fundamental things to do in statistics. And not only we don't really want to do it because that is like the second most fundamental thing, it's also fundamental because covariance has many applications. Okay, think about doing something with the data. You can think of doing principal component analysis in multivariate statistics. For that you need the covariance. You can think about doing regression. For that you need the covariance. You can think about doing classification. For that you need the covariance. Covariance is all over everything. You do whatever, covariance comes in. Okay, so this is a very fundamental problem in statistics. And also this is something that has been quite well explored in functional data also. Okay, so in particular, uh, there is this empirical covariance. So you know what the empirical covariance is, the sample covariance matrix is. If we have x1, x2, xn, then the sample covariance matrix would be to take, so suppose that the mean is 0. Okay, so the sample covariance matrix S would be 1 by n or n minus 1. Asymptotically, it doesn't really matter. Summation I equals 1 to n xi minus x bar xi minus x bar transpose. Okay, this is the sample covariance matrix or sample variance, sample dispersion matrix, sample variance covariance matrix, whatever you want to call this. If the mean is 0, we can also use that information and don't uh, take the x bar. We don't subtract the x bar. We just save 1 degree of freedom. We will use 1 by n summation I equals 1 to n xi transpose. This is something that we use if we know that the mean is 0. Okay. So if we know that the mean is 0, then similarly, so the outer product is denoted by this operator. So this cross surrounded by this circle. This is also, so this is something called a tensor product. Okay. So we just use that idea, take it here. We have the observations. We take their outer product, take the average of the outer products. That gives us the empirical covariance. This is again an operator, etc. Now this is something that can be used. This is like the most basic thing. It has also some nice properties. But now let us try to see what happens when we try to do this. I already told you that we never observe the data completely. We don't observe the data as functions. We only observe the data on some points. Okay. So just for the sake of simplicity, suppose that the data is observed on a k by k by k by k grid. Okay. What does that mean? So if we have 0, 1 power d, that means we have several indices. So u is a vector. That means it has some components u1, u2, ud. And each of them are taking values on 0, 1. Okay. By a k by k by k regular grid, we mean that on each of these axes, we have k many points which are equally spaced. So they are equidistantly spaced. And so over the whole domain, we have k times k times k times k to the power d many points. And we observe the function on each of these points. Okay. So maybe a easier picture to understand would be the case where we have d equals 2. So here we have u1, here we have u2. This is from 0 to 1, this is from 0 to 1, and this is like 1, 1. So this is 0, 1, 0, 0, sorry, maybe 1, 0, and this is 0, 1. Okay. So this is the surface on which, this is the plane on which we are going to observe the function. Now what we are doing is we are saying that this is subdivided into k many points, okay, which are equally spaced. And similarly, this part is equally divided into k many points. And now there are this intersection. So we have this whole space being partitioned into the small chunks. Okay. So here we have k points, here we have k points. So there are total k square many points, okay, k square many chunks in this whole space. And we are observing the function on once in each of these points. Okay. So this is for d equals 2. If we have d equals 3, it will be k cube, d equals 4, k to the power 4, and so on. For general d, we will have k power d many points. And this is for one function. We have n many functions. So in total, we have k power d many points for one function. In total, we have n times k power d many observations. Okay, this is our total observations, or this is the total degrees of freedom that we have. Okay. Now, if we want to estimate the empirical covariance, just go back to the multivariate setting. If we observe the data, so if our x is p dimensional, Then this is what? This is a P by P matrix. The sample covariance matrix is a P by P matrix. Okay. So it has P square many elements. Okay. Now, in our case, the observations are K power D. Okay. So we have K power D many observations. So each of this x's, they are like K power D dimensional. Okay. So the sample covariance, the empirical covariance or the sample covariance, the element that we have constructed here, in practice, it is going to be a K power D by K power D dimensional object. Okay. Is that clear? Okay.
So can I have a doubt here?
Yeah, sure.
So for D is equals to 2,
Hmm.
we will get a multivariate data as a special case.
Not
And
D equals to 2. No, even with D equals 1.
oh, D equals to 1.
Yeah.
So even multivariate and matrix variate data, what we call as a three-way data, is also a special case of these.
Matrix variate would be D equals 2.
2, yeah, that's what, yeah. Then, so you're talking about a tensor variate data where you are generalizing things.
Yes, so there is a small difference between that and this. Okay.
Okay.
So when you talk about matrix variate data or for instance, so let's take the multivariate data first. So D equals 1. When you have multivariate data, your data looks like this. You have x1, x2, xp. Okay. Now, when you have a data like this x1, x2, xp, this ordering, this doesn't mean anything. You can as well work with x2, x3, x5, x10. The ordering of the elements, it doesn't mean anything in general for multivariate data. Okay. But when we say we have a functional data, it means that there is a notion of dependence between the things, and the dependence is via some functional relation, which is not the case for multivariate data. For multivariate data, we don't say that there is a functional relationship between the things. The observation is now being observed as a vector or as a matrix because of our inability to capture infinite dimensional data. Okay. It is because we have to discretize. There is no other reason. So there is this fundamental difference. You cannot say everything is functional. For instance, it makes sense to say that the temperature curves is functional data because there is an inherent functional nature. Okay, so we are perhaps observing the data at 5-minute intervals. That is because we cannot observe the data always. We have to observe the data at some intervals. But
I have a question.
yes,
Can I say this?
yes.
Okay,
But
so
can I just
yes,
complete
sure.
the answer? Yes. But even when we are not observing the data, there is some value which we have missed, which is not the case with multivariate data. Similarly with matrix, variate, etc. Okay.
Yeah, okay, sir, got it. And
Yeah.
what kind of I can assume that a data point is an n-dimensional array here.
Data point is?
Each and every data point is an n-dimensional array. For example, in a multivariate setup, we have for a p-variate data, the data point is a p cross 1.
Hmm.
For a multivariate, it is n cross b for n rows and b columns.
Yes.
So for the higher dimensions, as long as I go, I call it as a p-dimensional array, each and every data point.
It's not quite that. It's more like for each of them, we have k power d many observations. Okay, so you can say that it's like a k power d dimensional object. But then if you just use it, you just vectorize it, then you somehow miss the notion of this the same problem that happens if you just convert a matrix into a vector.
Yeah, got it.
Yes, Angshumita?
Yeah, so I was, as you said, that the empirical covariance that we were going to have is k to the power d cross k to the power d dimension, right?
Yes.
So the problem that I mean, it is taught in our, I mean, curriculums that whenever there is in high dimensional data, there is a problem of getting isolated in the data point getting lost in the immensity. There is
In
a
the
problem
in the
immensity. For example, there is two-dimensional data. There is 3 data points. When
Mhm.
we are increasing the, I mean, the dimension,
Mhm.
the 3 data points would be maybe isolated points there, and we
Yes.
couldn't see any covariance between them. So
Mm.
how we I mean, solve that thing if we are
Yeah, so that is what I am going to discuss about. Okay, so I'm just formulating the problem now.
okay?
Okay, so here it is not real. So, okay, so there is a little bit of difference here. So one thing is, of course, what you said is correct. So if you have 3 data points in some, even not 3, even if you have 100 data points in say 200 dimensional space, then the data are like isolated. Okay, so whatever isolated means. So what happens is that the, anyway, you know what happens. So the data are always pushed to the boundary of the data cloud, etc. But what happens is, in this case, we rather have a problem of plenty. Okay, so what is happening? So let me come back to it, and I'll discuss this when as we move along. So we have a k power d by k power d object, which we are trying to estimate. Okay, k power d by k power d object. So the estimation, for estimation, we want what? We have to estimate all this k power d by k power d many elements. Of course, there are symmetries, but the order doesn't really change. The order remains the same. The order, it's of the order k power 2d. Okay. For storage, we need to store those elements. So we need the same storage. But then, what is happening? Yeah. But then, uh, it's not only about estimation and storage, we also have to use it. Like I said, that if we want to do principal component analysis, we want to do regression, we want to do classification, for all these things we need to somehow do either eigen decomposition of the estimated thing, or we want to have inverse of that element. For all this, the cost that we need is big O k power 3d. Okay, so you know that if we have a p by p matrix, there are p square many elements. So we have p square here. Similarly, storage is p square, and inversion or eigen decomposition, that takes order of p cube operations. So the same thing's happening here. Now the problem is this: when d becomes large, when d is 2, it's like big O k square, big O k square, big O k cube, which is still manageable. But as soon as d becomes large, all these things are getting much larger. Okay, and the problem is d is in the power. Okay, so it is going to increase exponentially with d, and that is a curse of dimensionality that we are going to face in our case. Okay, just to illustrate what happens, because this k, d, etc., this are not always clear. I showed you the fMRI data, the MRI data. So this is coming from this 1000 connectome project. It is, so MRI data, these are 3D images, and the images I told you, these are again discretized. These are of size 64 by 64 by 33. What does that mean? It means that we have 64 elements on one side, 64 elements on the other side, and 33 elements on the third side, on the z-axis. So the empirical covariance is going to be of the size 64 by 64 by 33 times 64 by 64 by 33. If we want to store this element, we would need something like 136 gigabytes of space. 136 gigabytes is not a matter of joke. Okay, so it's quite a lot. And not only that, we have to store it. Some of our computers have that much storage, but we have to work with this. So we have to store it on the RAM. Storing 136 gigabytes of thing on a RAM is not a matter of joke, because most of our computers has what, 8 or 16 or 32 gigabytes of space. Now the problem is really because of this multiplication, because if we only had 64, we would have required 32 kilobytes of space. 64 by 64 would have still required 134 megabytes. But the whole thing now requires 136 gigabytes. And see how from kilobyte, megabyte, we go to gigabyte, even by multiplying the small numbers 33. Okay. So the point that I'm trying to make is this number 64, 64, 33, they don't look very big. They are very small rather. And they don't even look scary. But when we multiply them, the multiplication effect can be very large. The same thing, it's the multiplication is very, it doesn't show us what the real numbers are. For instance, if we only had 10, even we had 10,000 observations uh, per curve, it would have still required 800 megabytes. So this multiplication, this leads to something like 1,30,000. Okay, so which is not clear when we see 64 and 33. And that's not the end of the story. The data is actually fMRI data, where this F stands for functional magnetic MRI. Functional means that the data is recorded continuously over time. So the actual data is 64 by 64 by 33, and they are continuously recorded at 225 time points. So the whole thing is actually a 4-dimensional object, and for that we need something like 7400000000 gigabytes of space. It is not possible. It's completely not possible. Okay, some other approaches. There are some other approaches. For instance, there is this notion of global smoothing or basis expansion. These are two different things. So for global smoothing, we first smooth the data points. So the data that we observe, those are discrete data. We first smooth them and work with the smooth data. Okay. The other option is to use a basis expansion. The other option is to use a basis expansion, where we just take a basis, expand the data with respect to the basis, and work with the basis coefficients. In this case, in both the cases, we first smooth them, then we just take some numbers. So the data is now reduced to multivariate data, and we work with the multivariate data. There are some problems with this, but maybe later we move on. The other thing is to work with what is known as local smoothing. So in this case, what we do is we just compute what are known as raw covariances. So we have observed the data at some points. We take the the product of xu and xv. Okay, these are what are known as the raw covariances, and then we use local smoother to estimate the covariance surface. This is another approach. Now, these two approaches are used in two different settings. One is known as dense functional data, the other is known as sparse functional data. Dense functional data is where we have a lot of observations corresponding to each of the functions. Okay, in that case, it is possible to smooth the function first, or take a basis and expand this and work with the expanded things. On the other hand, there is this notion of sparse functional data, in which case we observe each of the curves or functions only at a few points. Okay. In this case, it is not possible. The smoothing, if you do individual smoothing, because we have only a few observations, the smoothing is not going to be good. And similar things with this basis expansion. I mean, we somehow have to find these coefficients, and that is not going to be very easy. Okay. Now there is a very there are some problems, or there are some differences, stark differences between the two regime. In particular, when we have sparse functional data, then all the problems with k power d, etc., curse of dimensionality is not that strong. On the other hand, doing smoothing over a high dimensional domain is also not easy. It's not easy. It's usually not even good. And that is not also something that we are going to discuss about. The problem that we are going to consider is the problem of dense data, and we are going to discuss how to address this problem. Okay. Okay. So now, how do we tackle this? So it's not that I am the first one or we are the first one to tackle this problem. This problem has been long as existing. People have been used this. So what people have been using and what is the state of the art is this assumption of separability. What separability says is that the covariance that we are trying to estimate, that can be separated across dimensions. Okay, so C is a function of two arguments, U and V. This can be written as the product of C1 U1 V1 times C2 U2 V2 and so on times CD UD VD. So U has components U1 U2 UD, V has components V1 V2 VD. We take the first two components, define a covariance on that, take the second two components, define a covariance on that, and so on. The assumption says that the covariance that we are trying to estimate can be written as a product of all these covariances which are separated across the dimensions. Okay, this is why it is called a separable model. Let's see what happens to the numbers that we saw for the empirical covariance. If we want to estimate the separable covariance, estimation now requires d times k square many things, because we are trying to estimate d many functions C1, C2, CD. Each of them are being estimated on a k by k domain. Okay, so for each of them, we need k square many things and total dk squared. The same storage, and now manipulation, inversion, etc. For that, all we need to do is do the same operation on each of the components. That is enough. So for each of them, we need k cube operations. In total, we need d times k cube operations, which is much lower than what we had earlier. So this d was multiplied in the power before, which has now come here as a linear term. Okay, so this is the state of the art. This is what people have been using, and I would say this is a convenient assumption, because the things that it does, it just reduces all the complexity to a linear term in d. But there is a but. Okay, so nothing comes for free, and this is also not a silver bullet. This is demonstrably inadequate in a large area of examples. Okay, so people have been very skeptical about this assumption, and recently, it's quite recent, that people have actually shown that separability is not a good assumption to make. In fact, all the data that have been assumed to be separable and analyzed as being separable, in most of the cases, they have actually come up with tests for separability, and the tests are most of the times rejected. Okay, so separability does not hold in practice generally. But it is still the state of the art, and I would say that it prevails due to the lack of a better alternative. There is no better alternative to this, okay, even now. So this is where our work starts. We want to address this problem. We want to give a method to estimate the covariance, or equivalently the kernel, in a non-parametric way. So the assumption of severability is a non-parametric assumption. Because of some reason, it doesn't say what C1, C2, CD are. So the functions are completely unspecified. But at the same time, we want to do it in a computationally feasible manner. We want to do it in such a way that the thing that we get, it is easy to store and manipulate. But we want something that is more flexible than the separable model. Okay, this is where our work starts. Okay, and this is the alternative that we propose. We proposed what is known as the covariance network. Okay, what is that? We want to estimate the covariance C. We use C hat. The structure of C hat is like this. It is double summation over R and S, both ranging from 1 to R. Then we have some coefficients lambda RS. Then we have sigma WR transpose U plus BR times sigma WS transpose V plus BS. This is defined for UV over 0, 1 power T. Okay, this is the thing that we are going to use to estimate C. Okay, we call this thing covariance network. Here, this number R is called the number of nodes in the model. Sigma, this sigma function is a specified function. We say what the function is. We know what the function is. There is no problem of estimation of the function. We know what this is. We call this the activation function. And the parameters of this model are these elements, is this lambda rs, this vectors wr, the elements br. Okay. These are the parameters of the model. So all these things are the parameters. Now this lambda rs, if you look at it, we have lambda rs, r ranging from 1 to r, s ranging from 1 to s. So this can be put into a matrix, and we assume that this matrix, r by r matrix, is positive semi-definite. Okay. So these are the parameters of our model. And the assumption, so why do we assume that this matrix is positive semi-definite, is this covariance, we are trying to estimate a covariance. And similar to the multivariate case, the covariance of functional data is also non-negative. Okay, so the covariance of a vector is positive semi-definite. Similarly, the covariance operator corresponding to a functional data is also non-negative. And as soon as we assume that this matrix is positive semi-definite, it is immediate that this C hat that we are using, it is non-negative. Okay, which makes sense.
Soham,
Yes.
can I just small? So this big R, the number of nodes, is it known or unknown?
Yeah. So it is, when we are going to run this, this is going to be a parameter of our model. It is going to be a hyper parameter of our model. Okay. So we don't know this, but when we need to run this, we have to know this. And there are some methods of selecting this. I'll come back to this.
Okay.
Okay. All right. So the introduction was quite quick. This structure, it is not clear why we call this network, covariance network, and so on. Why these are called nodes, why this is activation, what are these learnable parameters, etc. So let me show you why this is a network, and let me try to convince you that this is a network. So this is what we are doing. Okay, so starting with U, we take W transpose U. So W transpose U means we we multiply the components of U by some numbers and then add them up. This is denoted by this picture here. So here are the components of U. An arrow means that this component is taken, and the number that is written next to the arrow, that number is multiplied to this number here. And then that product is stored in this point. Okay, so U1 is multiplied by something, U2 is multiplied by something, all the components are multiplied by something. They now come here. Now, whatever is in a node, whatever comes here, they are added. Okay. In addition, we have this node 1. So 1 is being multiplied by something. That means we only have this number. That is also coming to this point. So that is also being added. So the result is going to be WR transpose U plus BR. Okay. So that is stored in this point. Now you see a sigma here. That means whatever is in that point, we apply the function sigma on that. So the result here is WR transpose U plus BR, and we apply the function sigma on that. Okay. The same structure is repeated on the right side with V. So the components here are sigma W1 transpose U plus B1, sigma W2 transpose U plus B2, and so on, sigma W capital R transpose U plus B capital R. And here we have the same things, but with V instead of U. Okay. So we get these components. Now, this sum is just the cross multiplication of all these components after multiplication by the coefficients lambda. So we take cross multiplication of all the components that are here and all the components that are here, then multiply the result by these numbers. And again, everything that comes here, they are added. This gives us the final result. Okay. This is the pictorial representation of what we are using. Now, this is a network, because if you know what a network is a bunch of nodes and edges. So here we have these nodes. These are the nodes of our network. These are the nodes of our network. What is happening?
But BIs and WIJs, they are all same set for U and V both.
Yes, that we have the same structure here. Okay, for each of the nodes here, for
So the relationship comes through lambda IJs.
the relationship also comes through W and B. These are parameters of the model, which we are going to learn from the data.
Oh, for the same set for both U and V. Okay, I got it. Okay,
Yeah, so if you look at the structure, it's the same W and
Yes.
same B.
Yes.
So we have the same structure for U and V,
Right.
but then those are going to be estimated from the data.
That's a different, but correlation will be there. Nice.
Yeah, correlation will be there. Correlation
Yes,
will be there.
nice. The idea is fantastic. Okay, let's see. Thank you.
Okay. All right. So somehow this is not working, but it's fine. Let's move on. So these are the nodes, and then we have also the edges. So this is a network. Okay. So nodes and edges are there. And in fact, this is also something that is known as a neural network. Okay. So it's not that we can have any edge between any two nodes. You can see that there are layers of nodes, and we can only have edges between layers of nodes. For instance, only the topmost things, we can have edges from the topmost to the next one, and from that to the next one, and so on. So this is why we say that this is a network, and we say that this is a covariance network, because finally the thing that we get, that is a covariance. Okay, so it's as simple as that. We have a network which gives us a covariance, so it's a covariance network. Okay, and R is the number of nodes, because you see here we have R many things in this part. We have R many things. So this is why we say that R is the number of nodes in the model. This sigma is called the activation function because of the nomenclature from the discipline of neural networks. In that, this sigma function is known as the activation function. And you see, because we have the lambdas to be the lambda matrix to be a positive semi-definite matrix, it immediately tells us that the final thing is indeed a covariance. Now, what are the properties of this? It looks nice, but is it nice? So first of all, it is a non-parametric model, and you may say, what do you mean by non-parametric? It's completely specified by parameters. So what is non-parametric about it? So what is non-parametric about it is the following. There is this result, which is also something called the universal approximation theorem. It says that if you give me any covariance, C is any covariance function, then I can always give you a covariance network of the type that I have just shown, so that, and you give me a precision that I want this much precision, I can give you a covariance network of the type that I have shown, so that I can get as close as the specification that you have given to the given covariance. Okay. So it is always possible to approximate any given covariance up to any given precision using the structure that I have shown. So when we are constructing this thing, we don't assume that the underlying thing has a structure like this. So we are not assuming that the true covariance looks like this. But the reason why this works is because of this result, that any covariance can be approximated up to arbitrary precision using a structure like that. But there is a small requirement. We want the function sigma, the activation function, to be of a particular type. In particular, we want the function to be non-decreasing. The limit at -infinity is 0. The limit at infinity is 1. And this is satisfied for any distribution function. In particular, there is this sigmoid function, which is 1 by 1 plus e to the power minus t, which satisfies this property. Okay, Secondly, we wanted to do it efficiently and store it efficiently. Now, how do we estimate it in practice? How do we estimate the elements of the model in practice? So first of all, we define the sample covariance matrix, which I have already defined, Cn hat, which is the empirical covariance. And then we do the following. We take the covariance network and we find the parameters by minimizing the distance of the covariance network from the sample covariance matrix. Okay, that is what we do. Now, at this point, you may say, if you can do this, why not use the sample covariance, and why are you using this? If sample covariance is already quite expensive to store or estimate, and you are using that, and then you are trying to find a minimizer, etc., then what is the point of doing all this? The point is, this is only we are writing on paper. Okay, we don't need to do this in practice. It is only being written on paper. In practice, we don't need to construct Cn hat or even this G thing. Everything is computed based on the observations X and the structure that we have. Okay. So what we do is feed the individual fields instead of the covariance. What do I mean by that? We start with individual functions xn nn, which looks like this. It is sigma WR transpose U plus BR times xi nr and take sum over R. Okay. So these are what are known as neural networks, and these are neural networks with shared weights, because if you look at this, we have this for n equals 1 to n, and for different n, this part doesn't change. This part remains the same. It doesn't depend on n. Only thing that depends on n is this coefficient xi nr. Okay, so these are neural networks with this part shared between them. Once we do that, this G is taken to be the empirical covariance based on this fitted functions, fitted neural networks. Why do we use this formulation? First of all, if we know that R is smaller than n, then there is a 1-1 correspondence. Any covariance network operator can be written as the empirical covariance of some structure like this, and vice versa. Okay. Secondly, we have to minimize this thing, and to minimize this, we cannot use any known result. It's not that we are going to take the derivative of this with respect to G and set it to 0. That is not going to work. So what we do is we use what is known as the gradient descent. Gradient descent is a method to find a minimizer of a function for which other methods are not going to work that easily. So we want a function that is differentiable, which is the case for us. And for that, we can do it by hand, but we are going to use, what we have done is we have used modern computational tools that are available. So for that, we need to calculate the loss function, the function that we are trying to minimize, and its gradient. And interestingly, gradient calculation we don't have to do by hand. We can ask a computer to do it for us. Okay, so there are things called automatic differentiation routines which can do this for us, and it has some benefit over doing it by hand. So we do that. For that, all that we need to do is being able to write the function, the loss function, efficiently. If we can compute the loss function efficiently, then it is enough. The computer will do the other parts. With this formulation, I told you that we are trying to minimize this, but this can be written explicitly in terms of only the observations xn and the fitted observation xn and n, and it only involves inner products and nothing else. Okay, we don't need to construct these huge objects. That is only on paper. Okay, this is actually easy to calculate. So lastly, when we use this, because of how we have defined the covariance, it is a empirical covariance. So it is a covariance. So it is going to be non-negative definite. Ensuring non-negative definiteness over estimators is not easy. And by using this formulation, we completely bypass that. We ensured that the final result that we get is going to be non-negative definite. Okay. So this is what we do. This is our procedure. We fit this model. From that, we find, using gradient descent, we find this estimates of WR, BR, and Xi-NR by minimizing the loss. Once we have that, WR and BR are directly parameters of the model, and the other parameters lambda RS, they are obtained by this formula, which is nothing but the empirical covariance between the Xi R and Xi S values. Okay, so this is actually pretty easy to do. The WRs can be stored as a R by D matrix. The BRs can be stored as R vector. Lambda RS can be stored as R by R matrix. This is much lower than what we had earlier. We had earlier K power 2D. And now we have R by D, R by R. And in general, R is much lower than K power D. Okay. Now that's not the end of the story. We talked about other manipulations, and one thing to do with that is to take eigen decomposition. And in fact, the structure that we have taken that admits a closed form eigen decomposition in the following sense: any eigen function. So for a covariance, we don't have eigenvector, we have what is known as an eigenfunction. As because of the structure, the eigenfunctions look like the following. It's sigma WR transpose U plus BR, the same structure, and we multiply that by some number and add them up. Okay, so that is how all the eigenfunctions of the covariance operator look like. Now, how do we find this elements AR? They are found by doing what we do. So the coefficients are found by first of all maximizing this. So if you go back to multivariate setup, in multivariate setup, principal components are found by maximizing alpha transpose sigma alpha subject to alpha transpose alpha. The thing that is written here, this is equivalent to or similar to this psi transpose C psi, and norm psi square is 1. Okay, so same thing that we do in multivariate setup, just an extension of that to functional setup. Now what is interesting is this maximization, this involves what? C hat and psi hat, and psi hat, in psi hat we know that this part is known. Say WR, BR we have already estimated. We only want to find AR. And maximizing this subject to norm psi square being 1 reduces to maximizing A transpose sigma tilde lambda sigma tilde A subject to A transpose sigma tilde A equals 1. Okay. If we didn't have this sigma, then this would have been same as finding the leading eigenvector of the matrix sigma tilde lambda sigma tilde. Okay, but because we have this sigma tilde, this is not a eigenvalue problem. This is a generalized eigenvalue problem. And this matrices sigma tilde, lambda, sigma tilde, these are not difficult to find. These are all R by R matrices. So we have a generalized eigenvalue problem involving R by R matrices, which is very easy to solve numerically. You give the computer this matrices, it will solve it, this thing for you. There is a small bottleneck. What are these matrices? This lambda matrix we already get as a part of this estimation. The matrix sigma tilde we don't get as a part of the estimation. It is a matrix whose elements are this integrals. Integral sigma WR hat transpose U plus BR hat, sigma WS transpose hat U plus BS hat du. Okay, we know everything. We know sigma, we know WR hat, we know BR hat, etc. But finding this integral in closed form is not easy. Okay, but that is not a big issue. We know all these things. We can use any numerical method to approximate these integrals. In particular, Monte Carlo or quasi Monte Carlo methods can be used. Okay, so This we have used Monte Carlo to do this, and I'll show you how the results look like. But that's again not the end of the story. We also have theoretical guarantees associated to this whole procedure. In particular, we have two types of results: consistency and rate of convergence. I'll just go through that. Okay, so we have some assumptions under which we can show that this is our estimator, this is the truth. And I'll just mention that we are not assuming anything over C. Okay, so we don't assume anything about C. The result says that the expected error is bounded by twice the infimum plus this term. This infimum is the infimum over all possible covariance networks with given R and lambda n. Okay, so it says that our expected error is bounded by twice the best that we can do if we knew C. Okay, plus some other term which depends on the dimension but linearly, and the number of components that we have taken, etc. These are what are known as bias variance decomposition for the error. You can think of this as the bias of the method. So this is the best that we could have done if we had known C, and this is the bias that is happening because we are taking a model that is not the entire set. Okay, then we have a variance. It is coming because we are estimating components of the model. Okay, so but I don't want to discuss this in more details because of the time also. So I have shown, so this result is for some boundedness condition. This can be removed. We don't need this whole consistency thing. So the fact that CNR hat minus C squared, this converges in probability to 0, can be shown under the assumption that norm x power 4 is finite. And the bias term can be characterized under some assumptions, but that's not the point of this talk. Now there are some other things. For instance, what I have just shown you, that is what is known as a shallow network in the literature of neural networks. It is possible to extend this whole structure using deep networks. Okay, so shallow network means that, see, starting from U, we get this components only by applying this multiplication by constant, adding and applying this activation function once. When we have this thing happening once, that is called a shallow network. We can just do that again and again. If we do that again and again, that is what is known as a deep network. And we can do that here also. We can just do this multiplication, add them up, and again do the multiplication on the results here, and continue. We will have several functions, and then we can just take their cross product and add them up after multiplication by this lambda rs. That is what is known as a deep covariance network. Okay, the problem with this is that there are too many parameters. So this is prone to what is known as overfit. So it usually doesn't give very good results. To get good results, we need some kind of regularization, and this is what we do in the following. It is called a deep shared covariance network. So the difference between the previous one and this one is, here we had individual networks here. So things were happening individually for each of these functions. Here, we don't do individual things. We allow them to share weight among themselves. So there is a connection between all these functions here, except perhaps for the last one. The last function, the last coefficients are perhaps different. Okay, this is known as a deep shared network. Details I am skipping. Okay, so we don't have time for that, and it's not also very interesting. But what is interesting is this thing with this shared structure. It produces excellent results. I'll show that to you. Okay, so properties of both these things, they are again non-parametric. We have the universal approximation property, We again have efficient estimation and storage. We obtain the coefficients by minimizing the loss function as before. And in that the whole step, we don't need to form Cn hat or G as before. And we exploit the neural network structure heavily throughout. In particular, we draw heavily from the computational machinery that is available in computer science. Okay. Again, all these things admit closed form expression for the eigensystem. All we need to do is solve a generalized eigenvalue problem. We again have theoretical guarantees, in particular consistency and rate of convergence. I'll just show you some results. Let's skip the simulation. Okay, so yeah, so here are some results. You can see that this blue one is the deep shared one, the brown one is the deep one, the green one is the shallow one, the red one is the empirical one, and the cyan one, the sky color, is the best separable one, the separable covariance. So the red and the blue, so empirical and best separable, are always on top. This is relative error, so their error is always higher. And the left one is actually a separable model. So in this case, separable estimator is working very well. The right one is the same model, but we have rotated it, and the rotation destroyed the separability. And as soon as the separability is destroyed, separable model performs very poorly, and it's performing so poorly that we have to cut the picture in the middle. Otherwise, we would have had a very bad picture. So it's everything is under 30%, and it is somewhere around 60%, 65%. Okay. Same thing happens with another example. Here, the results are for new. This new denotes the smoothness and roughness of the underlying surfaces. So the underlying functions are smooth when we have large nu and rough when we have small nu. When we have rough surfaces, the empirical covariance doesn't work well. This is pretty well known. Let's go back to the functional MRI data. Okay, so the data that I showed you. This is how the data looks like. And let's look at the estimators. This is the estimated leading eigenfunction. So we have several eigenfunctions. This is the first, you can think of this as the first eigenvector. Okay. So this is the first eigenfunction using the separable model. This is how the data looks like, and this is what the eigenfunction looks like. Okay. So doesn't look that good. It's quite blocky. This is what we get using our model. Okay. So this reflects the underlying phenomena much better compared to the separable model. The same thing happens with the second eigenfunction, with the separable model and the model that we have, and the third eigenfunction for the separable model and the model that we have. So in particular, there are many salient features that are extracted by the model that we have proposed, which is not captured by the other models. And in particular, it is also quite interesting that these are data for resting state fMRI studies. So in that case, it is known that the functionality in the brain is quite symmetric, okay, which you can also see in this picture. You see that the picture looks quite symmetric. And it's very interesting that the pictures that we get, they are also very symmetric, which we didn't impose. It is something that the data, I mean, the model captured. We didn't impose any symmetry, etc. We are very happy with this result. We were very happy with this result, and finally, the journal also was very happy, and the paper was finally published. I'll come back to that. So to give a summary, we proposed covariance network to estimate covariance for functional data on high dimensional domains. And it has some useful properties. In particular, the model is non-parametric. Non-parametric in the sense that it is a universal approximator. It allows efficient estimation and storage. Throughout that, we exploited the neural network structure heavily. We borrowed strength from whatever advancements are there in machine learning. And it admits a closed form eigendecomposition, which allows us to easily manipulate and visualize the data. visualize the fitted covariance, and we have been also able to derive theoretical guarantees for the estimator. We have extended the thing to deep architectures, and all the useful properties are retained. In particular, we have excellent empirical performance, particularly using the deep shared model. Okay. All right, so that was the talk, and like I said, so we were very happy with the results, and eventually the referees of the journal were also happy with the results, and the paper was published in the Journal of the Royal Statistical Society in 2022. Okay, all right, so that's it. That's the end of this end of my talk, and I'll be very happy to answer questions that you have. Yes, I see a raised hand. Angshumita?
Yes. So actually, it is kind of a problem that I faced during my capstone project during my MSc.
Mhm.
So basically, what happens? I just want to give you a little bit brief about the data I have faced. So
Mhm.
it was a classification. The problem was to classify. I had to classify the light curves of the binary star system. So
Well,
not the
classify the
light curves of the
light
binary
curves. Okay. Hmm.
light curves of the binary star system.
Hmm.
So the y is here is the light curve of the each and every stars, and
Hmm.
x is the phases that what time it takes to complete a one rotation or two rotation.
Okay.
So the problem we came across is there is 1318 stars, and
Hmm.
each star have light curves which varies from 164 to 256. And when we plot these values, like phase versus light curve, each of them actually it can be shown that they are the functional data. I
Hmm.
mean, the phase is the function where y is the light curve. The
Hmm.
problem comes is each of them, when we are moving to one star to another star, the dependency actually changed with every time. So I was asking that if I can use the functional analysis in that space, because first we used a kind of like a parametric approach and
Hmm.
try to estimate it using Newton-Gauss numerical search. But I was thinking if there is any approach that we can use with using this
Yeah.
a
So,
functional approach.
without knowing a lot about the data, I cannot comment much. But I'm not sure whether the independent assumption is fine for you, but perhaps the identically distributed assumption is not correct, right?
No, it is not identically distributed. That is the
That
problem.
is the main problem. But
Yes.
even then, can you say that they have this? So you are saying that the covariance changes. So that means it's not even the setup that we are considering. So it's not sigma for all of them. It's rather sigma I, right?
Right. That is another problem. I think that would be like whenever we speak about, I mean, there must be a generalized way. So if you can guide me through that or any resources you can
Yeah.
mention.
So you are trying to classify a system, right? So
Right.
is it true that there are already data which has been classified into some system? So is there like a training data available?
So what I can say is the light curves that we have got from the for each stars.
Hmm.
Before that, in 2018, there was a study done by Shomita Modak and Ashish Kumar Chattopadhyay,
Hmm.
and they use interpolation for that y cap to generate new y cap from
Okay.
the phases. But the problem is they didn't consider the functionality between the phases and light curve. But it is obvious that the phase and light curves are the function of each other. Like
Okay.
there is a dependency. So I
Okay.
was thinking if there is a
No,
way
but
to
in that
use.
case, so what I'm not understanding is whether the problem that you have is a classification problem or a clustering problem.
Yeah, it's a clustering problem. I mean, we
It's
have
a
to
it's a
cluster.
clustering problem. Very
Right.
well. So there are some work on clustering for functional data. I have to admit that I am not an expert of that, but there are some works. Okay. But the problem is that if you think about things like k-means, if you
Right.
have like different variability, then k-means is not going to work very well.
We used a parametric approach for this, and you
Hmm.
used k-midioids. I mean,
K-midioids, yeah.
or partitioning around midioids, PAM
Hmm. Hmm.
used it.
Hmm.
I mean, we came across and we discovered there is 21 isolated outliers in the data, but it was
Okay.
for the parametric approach. And I
Hmm.
don't think the model that we considered before that was very convenient because it was not fitting well to the raw data.
Okay.
That's why I was asking if there is a way to use functional analysis for that, where every time the covariance actually changing, that this is not identically distributed, and these cases, if there is any way to
So
use this.
first of all, one thing that you can always do is you can use something called a Gaussian mixture model, which is again functional. There is functional versions of that, and that is non-parametric because functional data is infinite dimensional. So even if you have Gaussian data, that the Gaussian assumption, that is not parametric in that sense, and that I don't know how good or bad that is going to be. So that is one thing, but like I said, there are functional clustering methods, and I admit that I am not an expert of that. I don't know them very well.
But maybe you can give me some, I mean, resources and external resources that I could.
Yes, I can. I will try to send it to you. Okay, so you can just send me your email ID, or you can just send me an email. I'll try to send you some resources on that.
How can I send you the
Oh,
email?
my email ID is yeah. So my email ID is this. Uh, so did you find it? Can you see this? So my email ID is Soham Sarkar 1991 at gmail.com. You can send me an email
I got
and
it.
okay.
Yeah, I got it. Thank you so much.
Okay. Yeah. Any other questions?
I think, sir, there are no questions. If anyone have any question, you feel free to ask Dr. Sarkar. Okay, sir. Thank you for your insightful presentation.
Yeah. Thank you very much for having me.
Okay. So I think there are no more questions. We can end today's session. And I would also like to thank all the participants. And please stay tuned for details about the upcoming sessions. Okay. Thank you,
Okay.
sir. Hmm.
Yes. Were you saying something?
No, I think we can end the meeting now.
Okay.
I just
Thank you very much.
thank you for your presence.
Yeah.